Hello everyone. If you watched the last lecture, you recall that we analyzed this circuit, which is a first order RC circuit, just using our normal algorithm, wrote KCL equations for components, and then tried to reduce the number of equations to one that included only the voltage of this node, the capacitor voltage. And that equation, then we turned it into a differential equation with this format, for which we have the solution, and we solved it. But if you notice, that was kind of time consuming. It took me some time to do it for you also, as it requires some manipulation of equations, and now the equations are not linear, like simple linear algebraic equations, and rather you have to deal with the derivatives. So if you're not using a calculator, using this with hand and not using any trick and just directly going through the algorithm might end up being more time consuming than you can afford in some situations, maybe for an exam. Now, there are tricks that you can use to kind of bypass some of that math, and I'm going to go over that today to kind of show you how that's done. Everything starts with the assumption that this is a first order RC circuit, and you can turn all the capacitors in the circuit, if there are more than one, to an equivalent capacitor, and all the resistors to an equivalent resistor, which is the case here. And with that, therefore, all the voltages and currents in the circuit are going to have the same format, no matter which one you're looking for. So it's the voltage here, the current capacitor, current here, the voltage there, current there, voltage. Any of these are going to have the same format. And in order to solve that, therefore, all you need to know is the initial value for that parameter you're looking for, and the final value for the parameter you're looking for, and the time constant. So let's go through this process, and this time calculate VCT using that, bypassing a lot of math. So at t equal to 0, this has switched. This is VCT. I'm going to call that V1T, and this is my ground. Now, before the switch, we do the same thing that we did last time. So VC0 is basically just a voltage divider. The assumption is we have waited long enough for the capacitor to be considered an open circuit. In other words, there's no current passing through the capacitor because the voltage is constant, and derivative of a constant, which is the current, is 0. And with that, you're dealing with a voltage divider, so that would be 60 divided by 60 plus 20 times 40, which is 30 volts. So now that is the initial value that we need here for that equation. Let's do the final value this time. Now, for the final value, VC infinity, again, you're dealing with the same situation, meaning that you have waited long enough, everything has settled down, the voltage across the capacitor is constant, and therefore there's no current passing. So this part of the circuit is an open circuit, and in other words, there's no current passing here, so VCT and V1T are the same. Why is that? It's because if you write an equation for this current right there, I'm going to call that I1T, by the way. So I1 infinity is 0. So what is I1 infinity? It's VC infinity minus V1 infinity divided by 8K, and that's 0. So from this, you can see that VC infinity is actually equal to V1 infinity. VC infinity is equal to V1 infinity. So all I need to do is to calculate V1 infinity, which basically again is a voltage divider here, and this voltage right there is minus 75 volts. Why? Because that voltage minus this voltage is 75, and therefore that voltage is minus 75. So VC infinity, which is equal to V1 infinity, is equal to minus 75 times just a simple voltage divider. This is an open circuit, right? That would be 160 divided by 160 plus 40, which is 200, And that turns out to be minus 60 volts, which, if you remember, is the same voltage that we calculated, but last time we actually didn't directly calculate this VC infinity. We wrote this differential equation by combining the equation, and VC infinity was tau in the differential equation times K. So VC infinity was calculated as a result of doing the math, but here we are conceptually doing it by knowing the physics of the circuit and how capacitors behave over time. You could directly calculate VC infinity. Now, how about tau? Now, for tau, for first order RC circuits, it's equal to R equivalent times C equivalent. So if you have more than one capacitor or more than one resistor, you have to combine them to turn them into one equivalent circuit, multiply them by each other, and then that would be your tau. With this circuit, the C equivalent is just simply 0.25 microfarad. But the equivalent resistance is the resistance that is seen by this capacitor. Now, basically, you can put this all in the box, and then if you have a box with terminals coming off of it, to calculate the equivalent resistance, first of all, you make sure that, let me make that box a bit bigger, you make sure that all the sources inside that box are turned off. In other words, the voltage source is grounded. So the equivalent of this circuit becomes something like this. That's your 8K, and I'm looking in from here, right? That's 160K, and that's 40K. So now how do you calculate the equivalent resistance now? Well, the basics of it is that you put a test voltage here and look at the test current, divide the test voltage by the test current. That's by definition your resistance. But this is actually too simple to do, and you don't really need to do that. These two resistors are in parallel to each other because they share two nodes on the two ends, and the result is in series with 8K. So simply R equivalent is equal to 8 plus 160 in parallel with 40, which if you do the math, it turns out to be 40K. Okay, so now tau is equal to 40 10 to the 3 times 0.25 10 to the minus 6 microfarad. Divide everything by each other. That turns out to be 0.01, which is what we calculated before. So all that said, I can now directly write the solution for VCT. VCT is equal to VC infinity. I calculate that to be minus 60 plus VC0, 30, minus VC infinity minus 60 e to the minus t over 0.01, which is minus 100t, and done. So I skipped a lot of math and could quickly calculate the voltage across that capacitor. Now if you test this, you put t equal to 0, that becomes 1. These two go away, you get 30 volts. You put t equal to infinity, this becomes, this whole thing becomes 0, you end up getting minus 6. You can do this for any other parameter. Like you can do exactly the same for, say, this time we're going to do this current. I call it I2T. Let's do that for I2T this time. Now, again, you have to calculate the initial value of I2, final value, and then the time constant. So I'm going to clear this and come back and do I2T this time to see that you can do that for any other parameter. I just picked I2T, but you can pick any parameter that you want. Okay, so we want to calculate I2T this time directly using that equation. So again, we have to do circuit analysis before the switch. Same thing, so VC0 becomes equal to 60 divided by 60 plus 20 times 40, and that was 30 volts. So we know that before and then right after. Since this voltage is the voltage of a capacitor, the voltage before the switch and after the switch doesn't change. Now, Once we switch, now at 0, t equal to 0, I do circuit analysis for this part of the circuit and calculate I2 0. I need that because this time everything now I'm writing this for I2t, and therefore I need I2 infinity and I2 0 and tau for the same circuit. That being 30 volts, I can call that I1t and call this one I3t, and that's my node. I can write a KCL for that node and directly write the equations for the component within that KCL, so to do it faster, in other words. So it's I1, basically I1t plus I3t equal to I2t. That's what I need to write. So now I1t, now this is all written for 0. So let's make sure that all the equations that we write is at time equal to 0. I'm looking for I2 0. Initial value 0, 0, and 0. Okay, so I1 0 is VC0, which is, I'm going to actually not write it to skip steps. VC0 is 30. It's 30 minus V1 0 divided by 8 plus minus 75 minus V1 0 divided by 40 is equal to V1 0 divided by 160. Now multiply both sides by 160. That gives you, so 160 divided by 8 is 20 times 30, that's 600 minus 20 V1 0 minus 300 minus 4 V1 0 is equal to V1 0. Move all the V1s to the other side. That would be 25 V1 0 is equal to 300, and therefore V1 0 is equal to 300 divided by 25. And that is 12 volts. So now that I have V1 0, I2 0 is simply V1 0 divided by 160, which is 12 divided by 160, whatever that is. That's milliamp. Just keep that in mind because I'm writing everything as a function of voltage and resistors in kilo ohms, so that's milliamp. Great, I have I2 0. Now I move on to I2 infinity. Now, I2 infinity, relatively simple. Again, if you wait long enough, this turns into an open circuit, right? So this part is gone. This is the only circuit that you have, and I2 infinity at that point is equal to I3 infinity, and it's just the voltage divided by all the resistors, right? So quickly, maybe down here, I2 infinity is equal to minus 75 minus 0 divided by, so minus 75 minus 0 divided by 160 plus 40, which is 200. So whatever that is, that would be, say, minus 25, 3 divided by 25, 4. Actually 8, sorry. 3 divided by 8 milliamp. Okay, so I have I2 0, I have I2 infinity, and all I need is tau. Good news is tau is going to be the same thing that you calculated before. Tau doesn't change based on what parameter you're trying to calculate. It's still equivalent capacitor times the equivalent resistance. We've already done that. That was 0.01. So I just put it back in this equation. So I2t is equal to now I2 infinity, which is minus 3/8 milliamp, or which the whole thing is going to be milliamp. We're going to keep that in mind. Plus I20, which was 12 divided by 160 minus 3/8 e to the minus 100 t, and done. So I hope this have helped you understand a little bit more about the physics of what is going on with the circuit, as opposed to just focusing on the algorithm that solves the circuit. Even though that algorithm always is useful, if you're doing it with hand, sometimes it's kind of hard or time consuming. If you're using a calculator, you shouldn't mind. This would help you if you're trying to do the whole thing with hand. Thank you very much. I think we're ready now to move on to the next component, which is an inductor.